Pluto is a far-off and puzzling planet that was once an individual from our nearby planetary system's family. However, advancing upsetting declarations by leading astrophysicist deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They propose that this freezing world is on an expected brief course with Neptune. But how is this possible, and what might be the consequences of such a huge event? Are we witnessing a major celestial event, or is there something else to this impending catastrophe? Join us as we explore the potential consequences of a Pluto-Neptune encounter. Pluto, a former planet that was relegated to a dwarf planet status partly due to its eccentric orbit, remains a subject of interest and study in the astronomical community. As demonstrated by recent predictions by leading experts, Pluto's orbit is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential dangerous impact between these two planets that could pose a significant threat to Earth. But how could such an event even be possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, straying significantly from the nearly round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, which is set at 17 degrees to the ecliptic plane. The way Pluto orbits is much steeper compared to other planets. This tilt and eccentricity add layers of complexity to its orbital pattern. Perhaps one of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we might expect from their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its peculiar orbit. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep tilt and irregular shape. The mystery grew with the realization that Pluto's orbit indeed crosses Neptune's. The complexity of Pluto's orbit amidst these intricacies is proof of the complexity of space mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's path, and the Sun's gravity all work together in a complex way. The terms alpha libration and degree libration, along with the VZK influencing, are key to this conundrum. According to astrophysicists, what's keeping all planets in their orbits is a phenomenon called alpha libration. Concerning Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is located around 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from influencing each other. Expansion libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an additional layer of protection from potential collisions. Another significant factor in this situation is the VZK influencing, named after three scientists, von Zippel, Leo, and Kai, who studied how things move in space. It's about how three celestial objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling influences how they move. In Pluto's case, VZK helps us understand why its orbit around the Sun is so irregular. Despite Pluto's orbit appearing chaotic, this influencing helps keep it moving smoothly over long periods. The VZK influence shows that, although things in space might appear wild and erratic, certain patterns and rules maintain a level of control. These factors help stabilize Pluto's orbit, ensuring it doesn't collide with Neptune or lose its course. This three-body problem helps explain how these orbits change based on how these celestial objects pull on one another. Focusing on this helps us learn more about Pluto, our solar system, and distant stars and galaxies. Mathematical simulations in the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit is still relatively turbulent, with minor variations in initial conditions leading to massive differences over millions of years. However, these irregular properties of Pluto's orbit have been found to maintain stability over exceptionally long timescales, effectively keeping the chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection helps stabilize Pluto's orbit. However, Neptune isn't alone in this. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn contributes substantially as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable orbit for a long time, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to travel safely through space without running into trouble. These phenomena are essential when it comes to the universe, as they maintain the order and consistency of celestial movements. Without these forces, the solar system as we know it would be a much more chaotic and unpredictable place. Bodies like Pluto could collide with others or be ejected from their stable orbits, causing a cascading effect on other celestial bodies. For Pluto, especially with discussions about it potentially crashing into Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the dynamics of our solar system. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of stability through the complex exchange of gravitational forces and orbital mechanics. It also highlights the importance of ongoing observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the odd nature of celestial bodies, and Pluto's orbit is a perfect example of this phenomenon. The concept of orbital instability, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is strikingly demonstrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term trajectory in the vastness of our solar system. Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its structure and behavior. One of the most intriguing aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and other materials. The New Horizons mission, which flew by Pluto in July 2015, provided striking data about this distant world. The surface of Pluto is characterized by vast plains, towering mountains, and deep valleys. One of the most remarkable features is Sputnik Planitia, an epic heart-shaped plain primarily composed of nitrogen ice. This region exhibits a diverse array of landforms, including massive icebergs and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active, despite its significant distance from the Sun and its low temperatures. Another fascinating aspect of Pluto is its atmosphere, which is primarily made of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is thin but shows intriguing seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply orbiting Charon. This unique relationship contributes to the complex gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to other dwarf planets and potential impactors. This belt is a repository of ancient material from the early solar system, offering scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the developmental patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the key implications of understanding Pluto's orbital characteristics is the potential impact on how we understand the solar system's evolution. Gravitational interactions from neighboring giant planets like Jupiter and Neptune can alter the trajectories of objects in the Kuiper Belt, including Pluto, over time. This highlights the importance of studying these interactions to better understand the long-term dynamics of our solar system. Understanding Pluto's behavior in this vast and intricate dance of gravitational forces allows us to grasp the broader picture of the solar system's past and future. The interactions between Pluto, Neptune, and other large bodies have significant implications not only for the dynamics of the Kuiper Belt, but also for the development of planetary systems beyond our own. Pluto's unique position in the solar system has prompted many debates about its classification. While it was once considered the ninth planet, its reclassification as a dwarf planet by the International Astronomical Union (IU) in 2006 stirred controversy. This decision was based on the fact that Pluto does not clear its orbit of other debris, a key criterion for full planetary status. However, despite its reclassification, Pluto continues to captivate astronomers and the public alike, with its distant, mysterious nature and the ongoing study of its surface, atmosphere, and orbital dynamics. As we continue to explore and observe Pluto, its intriguing characteristics and the phenomena surrounding its orbit serve as a reminder of the complexity and unpredictability of our universe. The potential encounter between Pluto and Neptune, while unlikely in the near future, raises questions about the stability of celestial orbits and the forces at play in the cosmic ballet of our solar system. These questions drive scientific inquiry, pushing the boundaries of our understanding and offering new perspectives on the formation and evolution of planetary systems. In conclusion, Pluto's orbit is a fascinating example of the complex interplay of gravitational forces and the stability of celestial bodies. While the possibility of a catastrophic event with Neptune remains unlikely, the ongoing study of Pluto's behavior offers critical insights into the workings of our solar system. As our understanding deepens, it becomes clear that even the most seemingly unstable objects in space can achieve remarkable stability through the intricate balance of gravitational interactions. This knowledge not only enriches our understanding of Pluto, but also enhances our grasp of the forces that shape the universe around us.